All right, thank you, Frank, for that introduction. And of course, as Frank said, today is perhaps a particularly important time to be talking about this topic. I'm sort of shocked when I look at the news, and everybody is sort of shocked that this event has happened in Nepal and the impacts of the event in Nepal. And yet at the same time, we all know that events like this are actually very inevitable. And so why is there that disconnect? And what can we do to change that disconnect and to try and reduce the impacts of future events like that? And so that's what I'm going to be talking about. I'm going to be talking about a project to use a new technology to try and reduce the impacts of future earthquakes, specifically earthquake early warning. Before I jump into that, I want to acknowledge the wide group of people who have actually participated in this project. USGS, in fact, I saw Mary Lou Zobak across the room earlier this morning. When she was at the USGS, she was actually the first person to fund a research project that led to this. Cal OES, Berkeley, Caltech, close colleagues at Caltech have been working on this all along for the last decade or so. University of Washington, ETH Zurich, Southern California Earthquake Center, its director, Tom Jordan, is here today, and he helped to get this started. And then perhaps most importantly, frankly, the Gordon and Betty Moore Foundation, Vicki Chandler from the Moore Foundation is also here today. And they saw this project, saw an opportunity to take it to the next level and take what was a research project and turn it into an implementation. And that is very much where we're at today. Okay, so to talk about this, I'm going to, first of all, take you back to August of 2014, very early in the morning, and this is what happened.
Earthquake, light shaking, expected in 2 seconds.
So this, of course, is an actual earthquake early warning. This is a real one for a real earthquake. This was for the Napa Earthquake that occurred in the San Francisco Bay Area on that morning, a little less than a year ago at this point. And that was a real warning that was sent from our demonstration earthquake early warning system to the city of San Francisco, the Department of Emergency Management. And as you saw, I think they got about 9 seconds of warning. So we are talking about relatively short time frames. However, hopefully you will soon be convinced of the importance and the value of having that kind of time frame. Okay, so let's back up a little bit. What is earthquake early warning? And I'm actually going to cheat. I used to give hour-long seminars answering this question. Instead, we're going to answer that question in 3 minutes, and I can do that because I have somebody much better to do it for me. I'm going to have Rachel Maddow explain to you what earthquake early warning is.
Speed of light. Thanks to things like fiber optic cable, we can move information literally in a flash, and that is good, just in the abstract. But that is, it turns out, potentially less safe. If the information that you are moving at the speed of light is notification that an earthquake is about to happen. Earthquakes happen in a specific place in the ground, right? Earthquakes have an epicenter. But you don't just feel an earthquake at the epicenter. The shuddering waves of motion in the earth from an earthquake, they emanate out from the epicenter of the quake, traveling at the speed of sound. So if you had the kind of motion sensors that detected earthquakes, if you had seismometers along fault lines all over earthquake-prone regions, when there was an earthquake, the seismometers nearest to the epicenter, they could register that an earthquake has happened, right, feel the shake, and then they could send a digital signal at the speed of light, notifying communities nearby that this traveling at the speed of sound tremor, this motion of the earth, is about to arrive. This is not a way of predicting earthquakes before they happen. It's a way of basically warning people that an earthquake has just happened and that they are about to feel its effects. Brace yourself. But this thing works. Scientists at UC Berkeley say that their ShakeAlert earthquake early warning project, it set off an alert. It did go off this weekend, during this weekend's large quake in Napa, California. It was about to be felt in Berkeley, and this is the alert that told us so. Watch this.
Earthquake, light shaking, expected in 3 seconds.
They got a 10-second warning that they were about to feel a quake. And 10 seconds is not much time, right? But this brace yourself warning system, it works thanks to the simple fact that the speed of light is faster than the speed of sound, and earthquakes only move at the speed of sound. With more sensors in more places, they could presumably deliver even more warning time. California is hoping to have that bigger system in place in the next few years so they can get it funded and finished. From the LA Times today, once fully developed, the system could give downtown Los Angeles 40 to 50 seconds of warning that the big one was headed from the San Andreas Fault, giving time for elevators to stop at the next floor and open up, for firefighters to open up garage doors, for high-speed trains to slow down to avoid derailments, and for surgeons to take the scalpel out of the patient. Giving your surgeon enough time to get the scalpel out of you before the giant earthquake starts shaking the operating room. That idea of tectonically shaking the scalpel inside your body somewhere, that is something you can never unknow, and I'm sorry, but the idea that this works, that it worked this weekend, in fact. It's not just on a drawing board somewhere, it is in effect, and it could be expanded and is being expanded. That is an excellent thing. They've got a system like this in Japan, they've got it in Mexico, and some other places around the globe. California could get their whole statewide system done in a few years. God bless the geeks. They will save us all.
Just a little less scary.
Yeah, a little more scary. Maybe a little music or something.
I think you can see why I like this clip. Needless to say, I really did used to give hour-long seminars and I covered just the same material that she covers in 3 minutes. It's a little embarrassing. But the point is, of course, that this shows the system actually is feasible, it's possible. I'm actually not going to spend more than 2 more slides to tell you where we are with this system before I talk about the new developments. The way that this system works, the way that we were able to issue the Napa alert, was that we use 400 stations across California. These are part of multiple networks. This is the Berkeley Seismolabs network, a very broadband, high-sensitivity network. The USGS strong motion network in the urban environment, and then the strong motion network across much of Northern California. And then in Southern California, it's a joint Caltech USGS network of broadband instruments. All of these networks stream their data continuously in real time to 3 processing centers where we continually are looking for earthquakes, detect the earthquakes, locate the earthquakes, estimate the size of the earthquakes, and then obviously push out a warning for the earthquakes that really matter. So that's what the system looks like today. It's what we call our demonstration early warning system. It is not a public system. There is more work to be done before it can become a public system. But we are delivering these alerts to a range of users so that people can start to get used to the idea of using early warning, and frankly, so we can learn from any mistakes that we make along the way. And so just to give you a splattering of those users, City of San Francisco, I already mentioned, Los Angeles, of course, California Office of Emergency Services, Lifeline companies, Southern California Edison, PG&E, and then a range of other companies, Amgen, Google, of course, Google just takes everything. BART is notable because it's the first organization to actually implement an automated response. The BART train system in the Bay Area now automatically slows and stops their trains. And very quickly, I'll explain to you why they want to do that. During rush hour, they have 65 trains that are running. Most of them are 10-car trains carrying 1,000 passengers on every single train. At any given moment in time, there are between 40 and 45 trains traveling at 65 to 70 miles an hour. Many of you have traveled on BART. There are a lot of raised trackways, all kinds of things, hazardous environments for the train to be running along those tracks during an earthquake. So when they get their alert, the BART system is completely computer operated from a central control center. So when they get the alert, they can automatically bring all of the trains to a slow and a stop. It takes about 24 seconds for them to come from full speed to a complete stop at their normal deceleration rate. So you can imagine what would happen if just one of those trains was to derail at 70 miles an hour. So you can see why they've been so keen. They've implemented the automatic response, and in fact, in the Napa earthquake, the system activated Fortunately, there were actually no trains running at the time, so there were no trains that were stopped. However, their automated train stopping system did activate. So we're really making some significant progress, and as a result of that, we can really talk about substantial steps to a full-blown public system. That demonstration system I talked about, we started running it end-to-end in 2012. In 2013, California actually passed legislation saying that the state should build an earthquake early warning system. It actually passed unanimously, which is quite remarkable. However, you can see why. They actually didn't allocate any funding at the same time. Fortunately, US Congress has made slightly more progress. The Omnibus bill passed at the end of last year, allocated $5 million, so we can start the process of moving towards a public system, and I'm very pleased to say that the President's budget this year requests another $5 million. But to give you a sense of what we actually need, the total cost of running a public West Coast early warning system is about $16 million per year, plus a capital investment of $32 million. So there's still a long way to go, but you can look at that $5 million, and you can see it as being about a third of what we need to build that public system. So we are on the right path. We need to keep going, but I'm confident that we will actually get this public warning system built. Okay, so that's the system today, and I'm going to leave that and move on to improvements that we're trying to work on to make the system better for the events that perhaps matter the most, the biggest possible earthquakes. And in order to do the best job that we can for these, we need to go beyond the methodologies that we have built in place today, the methodologies that provided that alert in the Napa earthquake and other earthquakes like it. So the Napa earthquake was a magnitude 6 earthquake. It's what we think of as a point source earthquake. What we mean by that is you can simply treat it as a point in space and time, and you can talk about the shaking intensity as a function of distance from that point in space and time. That's fine for magnitude 6 earthquakes. It's probably okay for magnitude 7 earthquakes. Once you get to magnitude 8 earthquakes, and for sure magnitude 9 earthquakes, it is not good enough. We have to actually recognize the extent of the fault that is rupturing in the earthquakes. So of course we have magnitude 8 earthquakes in California, but I'm going to go up to the Pacific Northwest where we can see this issue, this problem even more acutely. They of course have these point source earthquakes. The Nisqually earthquake beneath Olympia was perhaps one of the more recent damaging earthquakes up in the Pacific Northwest, but they also have to worry about the megathrust earthquakes. The megathrust earthquake being, let's see if I can use this, being one, here we go, being one that runs all the way down the subduction zone, this purple region that you can see right here. And that can generate magnitude 9 earthquakes. The last one was in 1700. We know it has a recurrence interval of somewhere between 300 and 600 years, so we have to be concerned about an event like this. Now, fortunately, or unfortunately, depending on your perspective, we don't have data for these kinds of earthquakes from the US. So we actually have to go somewhere else to get the data, and fortunately or unfortunately, depending on your perspective, we can get this data from Japan. Of course, the magnitude 9 Tohoku earthquake of March 11, 2011 is the data that I'm talking about. A massive earthquake that ruptured the subduction zone, so very similar to the scenario we have to worry about in Cascadia. I'm sure you all remember the earthquake and the tsunami that followed it, causing a very large number of fatalities. Oh, that's interesting. Now, in Japan, they actually do have an early warning system. Their early warning system has been operating since 2007, and they were able to detect this earthquake and push out an alert before the shaking actually reached the coastline. What you can see up here is that warning. Oh dear, we're having some trouble. What you can see up here on this map is the warning region. So the star here is the epicenter of the earthquake. That's where the earthquake started. And then the red region is the region where they pushed the warning out to. However, they actually had strong shaking all down the coast of Japan here, including in the epicentral region where they did get a warning. But also down here, this is Tokyo, where they had strong shaking. And some of you may recall the striking videos of the skyscrapers swaying with respect to one another. So they had strong shaking down here as well. However, there was no warning issued to the region down here. Okay? So The Tohoku Earthquake, in terms of earthquake early warning, first of all, it was a success. I don't want people to lose sight of that. They did detect the earthquake, they did push out the warning, and so that was a major success on their part. However, it also revealed two limitations with treating earthquakes as point sources and using seismology-only approaches to provide earthquake early warning. Those two limitations were, first of all, that they underestimated the magnitude of the earthquake. So this figure shows the time from the origin time of the earthquake, and then the magnitude on the axis up here. And the dashed line is their estimate. They issued the warning right about here when it was a magnitude 7, and over time their estimate gradually increased, but the actual magnitude of the earthquake was a magnitude 9, the red line. So they were underestimating the size of the earthquake. The second problem was they treated it as a point source, rather than recognizing the finite extent of the fault, and that's why they only issued a warning in the red region because of its distance from the fault, when in fact Tokyo was in fact pretty close to the fault itself. Okay, so how are we going to improve this? One of the ways that we can do this is to use other types of data. Real-time GPS. It's the same GPS that you have in your smartphone, but using observation quality sensors that are permanently deployed, you have much higher accuracy, and you can actually start to detect the permanent offset of these sites during the course of the earthquake. And in fact, you can do it quickly enough to enhance the information that you have about the earthquake. So here's an animation. It's running in 2 times real time for this earthquake. The star is the epicenter. The yellow circle is the P waves that we use for our seismology-based system. The red circle is the S waves. That's when the shaking starts. But the period of strongest shaking is when you will see some red dots. It hasn't started yet. The green arrows, you can see the first green arrow, are when we're able to actually detect the beginnings of the permanent static offset on these faults. And you can see from the gray arrows they're going to get much larger than they are right now. We're 60 seconds into the earthquake at this point, and we've seen about 2 meters of permanent offset at those GPS stations that are closest. Now is the time that you also start to see the strongest shaking going on. You can see the big red circles. That's the strongest shaking in the region closest to the epicenter, and that obviously that strong shaking is going to propagate outwards from the epicenter, from the region of the fault. So the S wave arrived in Tokyo, but still there are, let's see, another 50 or so seconds until the strongest shaking actually arrives in Tokyo. So this illustrates a couple of things: the total time involved in these very large magnitude earthquakes, and the fact that we can extract the static displacement, the permanent static displacement, while the earthquake is going on. In fact, this is a simulation for real time of us with an algorithm that we've developed to separate out the shaking that the GPS sensors detect from the actual permanent static displacement. And that's what we can use to improve our earthquake early warning approach. Okay. Okay, so this is our one solution to those 2 problems. The first is that we come up with a better estimate of the magnitude. From that very first green arrow that you saw appearing on that animation, we start to get a better magnitude estimate. So now we're estimating a magnitude of 8.1 using that first GPS-based approach. It's a half magnitude larger than what the seismology-only based approach can do. But what is more important is that we can also use it to estimate the finite extent of the fault. Okay? And that's important because when we estimate the shaking intensity, it's a function of the magnitude and the distance from the fault, not the distance from the epicenter. So if I take my magnitude estimate of 8.1 and I estimate the shaking, this is what I get. If I also use this estimate of the finite extent of the fault that we can make, then this is the shaking intensity we get. Obviously, warm colors are stronger shaking. Now, you may not think there's a huge difference, but let me get you to focus in on this region. Of course, this is where Tokyo is, and this is where there was the biggest difference between the estimated shaking using point source versus using finite source. So this can make a really big difference. So as time progresses, of course, that was all the first GPS estimate. We can improve our information, we can improve our warning as time goes on. And in fact, the GPS-based approach can give us a very accurate magnitude estimate later in the time series, but frankly, it doesn't matter. What really matters for earthquake early warning is this first estimate very early in the whole process. So this is a very helpful approach that we need to use to try and improve what we're doing, but it's important to recognize that P waves are always going to give us the first detection and is going to give us the first warning. Okay, so this is what we should do. We should be using GPS. We've actually implemented this now in Northern California, and in fact it was running at the time of the Napa earthquake, and so it showed real potential. We're in the process of folding this in to the warning system, the demonstration warning system that I mentioned. Okay, still having trouble here. Okay, so we're going to do that. We're going to fold it in. So we have the seismology and the GPS. We have the P-wave-based approach from seismic systems that provides the first warning 4 to 10 seconds after the origin time. 15 to 30 seconds after the origin time, we start to get GPS information that we can fold in. And as time progresses, we improve our estimate and improve the warning of the shaking at greater and greater distances. So very quickly, but still, we can do better than that. And the reason that I think we can still do better than that is by better understanding the actual physics of the earthquake process itself. So here's another animation of a magnitude 8 earthquake on the San Andreas Fault this time. This particular earthquake is starting up at the northern end of the San Andreas Fault. This brown is the patch that is actually rupturing, and it's going to rupture all the way down past the San Francisco Bay region. The yellow line here is the P wave, the red is the S wave, which carries the strongest shaking. But it's not until this rupture itself travels past San Francisco that we get the strongest shaking and most of the damage will be done. So the big question that we have to ask ourselves is, how quickly can we estimate the final magnitude of the earthquake? Now, we all know, seismologists know that for a magnitude 8 earthquake, we expect on average perhaps in the order of 10 meters of slip on the fault. For a magnitude 7 earthquake, we would only expect to see about 1 meter. We also know that most of that slip occurs as this rupture patch is propagating along in the period of seconds or 10 seconds. So that would suggest that we could look at the fault up here. We should be able to see large amounts of slip and predict how big the earthquake is going to be. That is an incredibly controversial statement to make in the seismology community, that you might be able to do that. But the reality is we just do not have enough data to be able to answer that question. So if we want more data to answer that question, how can we do that? How do we go beyond the data sets that we have today to be able to improve what we can do? Well, so this is the seismic network that we're using as part of our demonstration system I already showed you. I want to zoom into a different network, a much denser seismic network in Southern California. This was a network that was put out by Nodal Seismic, an oil services company, a few years ago. And whereas we measure the station spacing for the networks that we use for our current early warning system in tens of kilometers, 10, 20, 30 kilometers, this has a station spacing of 100 meters. But what is truly remarkable is when you have data sets like this, you can see all kinds of effects that you cannot see, needless to say, when you have these much sparser networks. These are the seismic waves propagating across the network from a relatively small magnitude 3.4 earthquake that occurred off to the northwest in this particular diagram. The black line is actually one of the faults across Long Beach, and you can see the effects of that fault on the wavefronts as they're propagating across the region. This is the kind of data that we need in order to tackle those fundamental questions that remain outstanding with the physics of earthquake ruptures. And so what I want to propose, that one way of getting to that point, getting to these dense networks, is using smartphones. There's probably 200, 300 people in the room, and there's probably 200, 300 smartphones that all contain accelerometers sitting right in this room. So if we can harness those accelerometers and use them use the data both for science and to reduce hazards, we can make a really big step forward. How are we going to do that? Of course, we have to do it by using a cloud. So we have to, the challenge here is connecting your phone to my system. That's the challenge, is how do we actually harness it? But if we can do that, I could provide you with a warning, and you could provide me with a mass of data that we can be using, of course, not only to generate the warning, but also for all kinds of fundamental research that we would like to do. I've obviously run out of time, so I'm not going to spend a lot of time justifying why this is possible, but this is possible. Can smartphones record earthquakes? I'm going to very quickly show you this one example. This is 24 hours of data from one smartphone at the time of the Napa earthquake. Okay, this is a quiz. When did the earthquake occur? minutes. Okay, I'm not going to wait that long. So on the left-hand side, of course, this is actually a phone that was in a student's pocket. On the left-hand side is when that student was walking around all day long. I told you at the beginning the earthquake occurred at 3:20 in the morning. So the earthquake actually occurred here. Those of you with really good eyesight will be able to see a tiny, tiny little blip right here. But if I blow up this minute worth of data, so this is now 100 seconds of data, you can see the seismic arrivals for this particular earthquake. Yes, smartphones can be used to record earthquakes. So this is a project we call MyShake. What we know at this point is that smartphones can record earthquakes. Essentially anything with a magnitude greater than 5, if the smartphone is within 10 kilometers of it, we can use the accelerometer in your phone to record that earthquake. Most importantly, we can distinguish those earthquakes from other everyday signals, the ones you saw on the left-hand side of the previous slide. And we can do that with a remarkable degree of accuracy just on your phone. But of course, then if we think that your phone has felt the earthquake and it sends its information to a back-end server, we can be really certain that there is an earthquake going on. So where are we right now? We have a proof of concept. We actually had a rollout, a very quiet rollout. A not quiet rollout is the kind of thing that kills these projects. We had a very quiet rollout at the end of 2014, about 100 phones for students across the Berkeley campus primarily. And so they've been running it since. Their phones have been triggering on what they think are earthquakes, sending the data, providing more data for us to look at this. And we're hoping for a public release later this year. But the potential here is huge, okay? If we can do this, if we can figure out how to harness these networks, we can roll this out in various places around the world, which of course brings me to, I couldn't not talk about the Nepal earthquake, 2 slides. I couldn't not talk about the Nepal earthquake. And so I'm going to do that very quickly and just show how this lays into or plays into what I've just been talking about. So here's the New York Times map for this particular event. The epicenter of the earthquake is right here. These are the regions of the aftershocks. This is Kathmandu right about here. You've all seen the images of the damage to the city of Kathmandu. I guess the number of fatalities right now is up at getting close to 4,000. So what if we had an early warning system in this region? What could it have done? I mean, that's the key question. So the distance of the epicenter from Kathmandu is about 80 kilometers. So if you took that ShakeAlert system we're running today on the west coast and you put it down in Nepal, then they would have had about 20 seconds of warning in Kathmandu, first of all. So that's the first thing to take away. Second thing to take away is what's our ability to use this earthquake to understand the nature of the rupture. This is an initial map of the distribution of slip that occurred in this earthquake from the US Geologic Survey. As far as I can tell, there are no seismometers in Nepal. I'm sure there are a few, but I cannot find information about any seismometers in Nepal. So to do this, they use data from greater distances, teleseismic distances, to estimate the distribution of slip. This map of slip is telling us about the fundamental processes, and you can see it's on a very coarse grid for what is a very large magnitude earthquake. So there are no seismometers in Nepal, as best as I can tell. However, in Nepal, there are 6 million smartphones by current estimates. Okay? In the city of Kathmandu, there are 600,000. So if we could harness those phones, not only could we provide warning, but we would have a data set that would allow us to understand earthquakes. Okay, so in summary, earthquake early warning is possible. The challenge here is to put it in place before the next earthquake happens. More data is better warnings. That's true for GPS. I think smartphones are next. Seismologists don't make many predictions. I'll predict that smartphone networks are going to be what's next. And then the fundamental science questions that remain can be answered, including fundamental aspects of the earthquake rupture. So we have this rather sort of positive environment where having these dense geophysical networks will allow us to answer our science questions, and we may actually save some lives in the process. Thank you very much.
Thank you.